So the first question is, realistically, how precise can you expect to model a real building?
Yeah, that's there are hundreds of scientists trying to model real buildings based on monitored data. And the idea is to try to obtain this parameter. I told you, heat loss coefficient, UA values, and CVs. They want to get to the 10% of uncertainty. The thing is that when you measure these signals, each signal is taking an uncertainty within it. And the indoor temperature has an uncertainty and uncertainty. The heat provided to the building through the heating, it has an uncertainty. The electrical gains, another. And when you put them in these methods that you be learning in the webinars, you will see that those uncertainties, they combine and you obtain some parameters with a final uncertainty. And that final uncertainty, now it's bigger than the 10%. Yeah. To achieve this 10%, you need very good measurements, and a part of very good measurements, you need very good modeling techniques. Yeah, both things permit you to reduce the uncertainty of the estimates. Okay, how do you choose the position? I go answering now. Q2.
There you go. Yeah. How do you choose the position of the sensor, temperature, and?
Okay. In this, when you test building components with the puzzling methodology, they provide you some specifications to make this 3D monitoring of the indoor air volume of this test room, and that way, in the indoor air temperature, you consider the effects of the stratification and the effects of the variation of temperature within that volume of the air. But if you have buildings, real buildings, when you install the temperature sensors or the CO2 sensors, then there is no a perfect place. Yeah. We have done some research quite deeply, and we take a thermal zone of this building I told you, and when I show you in the presentation, and when we put in a thermal zone, I don't know, up to 18 sensors randomly in different positions, we see that the uncertainty of the indoor temperature measurement is about 1.2 degrees. And the uncertainty of the sensors was 0.1 degrees. So that's the where to measure the indoor air temperature. There are some obvious things. You cannot put it where the solar radiation strikes directly. You cannot put in a wall that is a facade wall, because then the temperature of the wall is affecting the air temperature measurement. So you have to put it in a wall that is an interior wall of the building, and it must avoid air currents, and it must avoid, very important, radiation, direct solar radiation strikes. And you cannot put it next to heating devices or devices that are producing a lot of heat. Yeah, that's the idea. And the height of the sensor must be about 1.5 meters, yeah, in normal rooms. Okay, question 3.
A third question is, if the heat transfer through thermal bridge can be 50% of total transmission losses, why are they ignored?
Yeah, this is a very good question, but if you are using, yeah, this is a key question, because if you have thermal bridges, it might be that the UA value of the whole building envelope, including the thermal bridges, it's much bigger than the UA value in the design phase of the building. This is if in the design phase of the building you didn't consider correctly the thermal bridges, then the real UA value will be much bigger than the theoretical design UA value. And the good thing of the techniques you are learning here is that when you use the modeling approaches to obtain the heat loss coefficient of the building that contains within it the UA value, and it's possible to break the heat loss coefficients into the UA and the infiltration ventilation heat loss coefficients. When you obtain that experimental UA value of the building that is already being used, do you see that the heating demand is used to calculate these UA values with the modeling techniques? And the real heating demand is considering the real effect of the thermal bridges. So the real heating demand will be bigger than the design heating demand. So using these techniques will permit you to obtain the real UA value that also considers the thermal bridges effect. And then, yeah, if you can go to the architect and you can say, hey, you were not, the real UA value is much bigger than the design one. And probably the architect will say, very good, and bye-bye. But at least you will know that the UA value of the building is not the design one. If these techniques are developed further, they will end up being necessary to certify the building behavior once it is in operation. And if it's introduced, if they are introduced in the standard of each country, then if you identify that your real UA value is much bigger than the design value due to thermal breaches or due to other problems in the building envelope, then it will be very useful because the architect will have to respond or the construction company or the architect, it will depend who is the one that is the responsible of this discrepancy, will have to respond for that discrepancy between the real UA and the design UA. A ver, Q4. I hope I am answering you. You cannot discuss me, so it's very easy to answer like this.
They can ask other questions and complete their question in the Q&A if they want to. So. Yeah,
if I don't respond you correctly, you can ask again, and the 30th of September or whenever it's possible, I will answer you. Yeah. Are there sensors that calculate the thermal comfort levels of a building according to a specific model, or we have to calculate it by collecting its parameters? I don't get really good the question, but for the thermal comfort within a building, we usually use these mean predicted vote techniques that they tell you, knowing the indoor temperature, knowing the relative humidity, which is the percentage of the average population that will be in comfort. So basically, measuring indoor air temperature and measuring indoor relative humidity, you can expect if the people within those buildings in those conditions will be in comfort or not.